When people first encounter Amazon Web Services, the reaction is almost always the same: overwhelm. There are hundreds of services, each with its own name, pricing model, and documentation rabbit hole. It feels like you're supposed to memorize an encyclopedia just to deploy a simple app. But here's the truth that rarely gets said out loud. Most real systems on AWS are built from a relatively small set of core services, not because the others are useless, but because these core services solve the fundamental problems every distributed system has to solve. Once you understand those problems, the services stop feeling random. They start to feel inevitable. AWS isn't a pile of tools. It's a collection of building blocks. Each one exists because at scale, something breaks if you don't handle it explicitly. Let's walk through the services that show up often in real architectures and why they exist. Everything starts with compute. At some point, code has to run. On AWS, the most fundamental compute service is EC2. Elastic Compute Cloud sounds abstract, but conceptually it's simple. EC2 is a virtual machine. You get an operating system, CPU, memory, disk, and network access. You decide what runs on it. You manage the lifecycle. EC2 exists because sometimes you need full control. You might need a custom runtime, a specific OS configuration, background processes, or long-running services that don't fit into an event-driven model. EC2 is the closest thing AWS offers to a traditional server, just without the physical hardware. But EC2 also exposes a core truth of distributed systems. Servers fail, they reboot, they disappear. On AWS, instances are disposable by design. You're not supposed to treat them like pets, you're supposed to treat them like replaceable units. That idea leads directly to the next layer, load balancing. If you have more than one EC2 instance, you need a way to route traffic to them. That's where elastic load balancers come in. Whether it's an application load balancer or a network load balancer, the purpose is the same: accept traffic at a stable endpoint and distribute it across multiple backends. Load balancers aren't just about scaling, they're about resilience. If one instance fails, traffic shifts. If you deploy a new version, traffic moves gradually. Without a load balancer, every deployment becomes risky. But not all compute on AWS looks like EC2. Lambda exists because managing servers is work, and much of that work has nothing to do with your actual application logic. Lambda flips the model. Instead of running a server and waiting for requests, you write a function and AWS runs it when needed. Lambda is event-driven compute. It exists for workloads where you don't want to think about machines at all. You care about responding to events, not maintaining infrastructure. HTTP requests, file uploads, scheduled jobs, queue messages, Lambda shines there. What's important is not to frame EC2 versus Lambda as a competition. They solve different problems. EC2 is about control and long-lived processes. Lambda is about simplicity and elasticity. Real systems often use both. Once you have compute, you need storage. The most foundational storage service in AWS is S3. Simple Storage Service is one of those services that seems boring until you realize how central it is. S3 is not a file system, it's object storage. You store blobs of data, each identified by a key, and AWS guarantees durability at a scale that would be absurdly expensive to build yourself. S3 exists because disks fail, data centers fail, regions fail. S3 is designed so that your data survives all of that. That's why it's used for everything from backups to static websites to data lakes. A lot of architectures quietly orbit around S3. Logs land there. Build artifacts land there. Machine learning pipelines read from it. Even services you wouldn't expect use S3 under the hood. But S3 is not for everything. Sometimes you need block storage attached to a machine. That's where EBS comes in. Elastic Block Store provides disks for EC2 instances. It behaves like a traditional disk, but with replication and managed durability. EBS exists because some applications expect a file system. Databases, for example, often want low-latency block access rather than object storage. EBS gives you that without tying you to a physical drive. And then there's EFS, the Elastic File System, which exists for yet another reason. Sometimes you need shared storage across multiple machines, a file system that many instances can mount at once. EFS fills that niche. especially for legacy applications or workloads that weren't designed for object storage. Compute and storage alone don't make a system. You need networking. At the heart of AWS networking is the VPC. Virtual Private Cloud is the logical boundary that defines your network. Subnets, routing tables, gateways, and security groups all live inside a VPC. VPCs exist because at scale you can't treat networking as an afterthought. You need isolation, control, and predictable routing. AWS gives you a virtual network that behaves like a private data center, even though it's fully software-defined. Once you have a network, you need to control access. That brings us to IAM. IAM is arguably the most important service in AWS, and also the most misunderstood. Identity and access management exist because everything in AWS is an API call. Starting a server, reading from S3, writing to a database, it's all authenticated and authorized. IAM is how you decide who can do what: users, roles, policies. It's the security glue that holds the entire platform together. Without IAM, AWS would be unusable at scale. What makes IAM tricky is that it's extremely powerful. You're not just granting permissions to humans, you're granting permissions to services. EC2 instances assume roles. Lambda functions assume roles. CI pipelines assume roles. Once you see that, IAM stops being a checkbox and starts being a design tool. Now let's talk about data. Most applications need a database. On AWS, the most common starting point is RDS. Relational Database Service exists because running databases yourself is painful. Backups, patching, replication, failover. RDS handles that so you can focus on schema and queries. RDS supports familiar engines like PostgreSQL and MySQL, which makes it appealing to teams that want managed infrastructure without changing their data model. But not all data fits a relational shape. DynamoDB exists for a very different reason. It's a key value and document store designed for massive scale and predictable performance. You don't join tables, you design access patterns. You trade relational flexibility for throughput and reliability. DynamoDB is used heavily in systems that need to scale effortlessly and tolerate bursts. It's common in event-driven architectures, user session storage, and systems where availability matters more than complex queries. Real architectures often use both RDS and DynamoDB, each where it makes sense. Once you have compute and data, systems start talking to each other. That's where messaging comes in. SQS exists because direct communication between components is fragile. If one service is down, everything backs up. Queues introduce buffering. They decouple producers from consumers. SQS is simple, reliable, and boring in the best possible way. You send messages, workers process them. If a worker fails, the message becomes visible again. This pattern shows up everywhere because it absorbs failure gracefully. SNS exists for a slightly different reason. It's about fan-out. One event, many subscribers. Notifications, alerts, event propagation. SNS is how you broadcast something without knowing who's listening. Modern AWS architectures often layer these services. SNS publishes an event. SQS queues receive it. Lambda functions or EC2 workers process it. Each service does one thing well. As systems grow, visibility becomes critical. That's where CloudWatch comes in. CloudWatch exists because you cannot manage what you cannot see. Metrics, logs, alarms. Without observability, distributed systems are opaque and fragile. CloudWatch aggregates signals from across your infrastructure so you can understand behavior, detect failures, and respond. Closely related is CloudTrail, which records API calls. CloudTrail exists because in a system where everything is an API call, auditability matters. When something changes, you need to know who did it and when. Deployment is another core concern. Elastic Container Service and EKS exist because containers changed how applications are packaged and run. Instead of managing machines directly, you manage containers. ECS is AWS's simpler container orchestrator. EKS brings Kubernetes to AWS for teams that want portability and ecosystem compatibility. These services exist because at scale, scheduling containers manually is not viable. You need orchestration, health checks, rolling deployments, and service discovery. And finally, there's infrastructure as code. CloudFormation and tools built on top of it exist because clicking around the console does not scale. Infrastructure needs to be versioned, reviewed, and repeatable. Whether you use CloudFormation directly or something like Terraform, the idea is the same. Your infrastructure is code. Once you step back, a pattern emerges. Most AWS services exist because some assumption breaks at scale. Machines fail, networks partition, humans make mistakes, traffic spikes. Systems need isolation, observability, and automation. The most useful AWS services are the ones that address those realities head-on. You don't need to memorize AWS. You need to understand the problems it solves. Once you do, the service names stop being intimidating. They become tools you reach for intentionally. That's the mental shift that separates struggling with AWS from using it effectively. If you understand compute, storage, networking, identity, data, messaging, and observability, you understand the backbone of most real AWS systems. Everything else builds on top of that. AWS is big, but the core ideas are surprisingly small, and once you see them, you start seeing them everywhere.